Okay, we're going to finish up our rotational solids today. We're going to look at part 3. So we've already looked at two methods. We'll just very quickly review those. We had the disk method. This was used when there were no hollow parts in the three-dimensional shape when we did our revolution. Then we had our washer method, which you can use when there are hollow parts. And with both of those ones, let's see, how can I do this? I'll put a little something like this, right? For both of those ones, you're going to use rotational radii that are perpendicular to the axis of rotation. You know what I'm talking about? For example, if this was our coordinate plane, and if this was our shape, maybe it was some kind of parabola or something, and let's say we were rotating it across the x-axis, then our rotational radii would be perpendicular to that axis of rotation, right? That yellow line's the axis of rotation, and our rotational radii would be perpendicular to it. It would be like this. That's the rotational radii. Now, the new method we're learning today is called the shell method. It can always be used, right? Doesn't matter if there's hollow parts or no hollow parts, you can always use it. And for this, there's not a rotational radii, there's a representative radius. So the difference with this is it extends from one edge of the area being rotated to the opposite edge, and it's parallel to the axis of rotation. So if I go back to my drawing up here, if I was going to draw the representative radius, it's actually parallel to the yellow line. It would go from one side of my curve here to the other. So this would be the representative radius. So yeah, that's the big difference. Rather than being perpendicular, this radius is parallel to the axis of rotation. So let's get right down to our formulas. Again, I have two for you, depending on whether it goes around the x-axis or the y-axis. So if you rotate it around the x-axis, the formula is going to be v equals 2 pi. Then we have our integral that goes from a to b. And we have a y, I'll explain what that is in a second, times h of y, I'll explain what that is in a second, dy. We're integrating in terms of y. Okay, let me write the second one as well, and then I'll explain things. So if it's around the x-axis, you can probably guess the 2 pi is the same. Again, a to b. It's not going to be y this time, it's going to be x. It's not going to be h of y this time, it's going to be h of x. It's not going to be dy this time, it's going to be dx. So let's explain some of this stuff. First of all, the h of y or the h of x, that's a function that describes the length of the representative radius. Okay, so that's for the h of x and the h of y. Now, for this y and this x, those refer to the distance from the representative radius to the rotational axis. And we're just going to have it be x and y. And the reason I can just make this x and y is because I'm going to make sure it's always rotated around the x-axis or the y-axis. So if this wasn't the case, if it wasn't always around the x-axis and y-axis, I'm sure you're going to do questions like that at university, it would just be a little bit difficult. You might have to subtract some amount. Like if it was rotated around the line y equals 1, then you might end up like with some amount like where you have to subtract 1 or add 1. It depends. Anyway, we're just going to, give you the gentle introduction this year. So we're always going to call this y, we're always going to call this x, but what those actually refer to is the distance of the representative radius to the rotational axis. Okay, let's try a couple questions. Okay, rotate the area bounded by y equals x cubed plus x equals 2, and the x-axis around the y-axis, and calculate the volume of the solid of revolution. Okay, that's a lot of stuff there. Let's draw our coordinate plane, or some of it, and it's going around, well, let's start with this, the x equals 2. So I could definitely draw that right away. Here's 1, here's 2. So we would have a line straight up from there. So it's bounded by x equals 2. It's also bounded by the x-axis, so we're going as low as this. So what the heck, I can put that. And now I guess I need to graph the y equals x cubed plus x. Also, it's going to be revolved around the y-axis. So this is my axis of rotation right here. Okay, let's graph this. Well, we could figure out what it looks like, but let's just plug in our 0, 1, and 2 and see what happens. If we plug 0 in here, you get 0 cubed is 0 plus another 0. Oh, 0, 0. One of our points is 0, 0. So right here. Okay, another point, if we put 1 in here, 1 cubed is 1 plus another 1 is 2. So 1, 2, I'm just going to write that point down because I don't know how high to go yet. And if I put 2 in here, 2 cubed is 8 plus another 2 is 10. So 2, 10 is another point. So I want to go as high as 10. I'll put it up there. And 2 would be way down here somewhere. I don't know, like that. So let's graph that. 1, 2 is here. And 2, 10 would be around here. And now we have our graph. And what we're interested in is all this area in here. Okay, so we're taking this blue area here and we're rotating it around the y-axis. Can you picture what that would look like? Does it kind of look like a bowl or something like that? And now we need to draw a representative radius. Remember, it's going to be parallel to this right here. It's going to be parallel to the axis of rotation. So, I don't know, I'll put it right here. This is my representative radius. Okay, let me write down the formula. First of all, we're rotating around the y-axis, so make sure you pick the right one, right? We're using this bottom one right here that has the x's in it. Okay, so we've got v equals 2 pi. Now, what are our bounds here? So we're doing everything in terms of x, so we need to look on the x, and it goes from 0 to 2. So those are our bounds here, 0 to 2. Now, x, remember, is the distance of the representative radius from our axis of rotation. In other words, our x amount is from here to here. And, well, it's along the x-axis. We could just call that amount x. And as I said, we're always going to call that amount x for this year. If this wasn't rotating around the y-axis, if it was rotating around this point right here, 1 for example, then it would be x minus 1, wouldn't it? So it's not that much more difficult, but I'm just going to keep it with just x and y this year. So it's just going to be x. That's the distance from the axis of rotation to the representative radius. Okay, now, h of x. We need a function that describes the length of the representative radius. Well, the length of the representative radius is always just equal to whatever your output value is of this function right here. The underlined one right there, the x cubed plus x. So that is your h of x, x cubed plus x. And this is in terms of x. We're going to integrate. Okay? Hard part's over. Figured out what numbers to input. Now we just do this. So 2 pi, I'm not going to do it yet. I'm going to do a little simplifying. Distributive property, you get x to the 4th plus x squared dx. Now we can actually integrate. V equals 2 pi. Integrate this, you get x to the 5th over 5 plus x to the 3rd over 3. This is from 0 to 2. So v equals 2 pi. Put 2 in here. 2 to the 5th is 32 over 5 plus 2 cubed is 8 over 3. And then we would subtract, and we plug 0 in here. Well, that's just 0 plus 0, so that's not going to make a difference. So all we have to do is add these two initial fractions. So common denominator is 15. Multiply top and bottom of the first one by 3, and you get 96. Multiply top and bottom of the second one by 5, and you get 40. So we have v equals 2 pi, and then 96 plus 40 is 136 over 15. And finally we can multiply the top by 2 pi. What's twice 136? 272. So you get 272 pi over 15. And yes, that is in lowest terms. Alright, let's try one more. Of course, this time we're going to rotate it around the x-axis. You know I'm going to do one of each. So calculate the volume generated by rotating the area bounded by y equals root x and y equals x cubed about the x-axis using the shell method. So basically it doesn't tell us, how far we should do this. You want to do it until the two meet each other. We're going to make some shape where they enclose each other. So you want to know when do they have the same y values. When does root x equal x cubed? Well, let's square both sides. If you square both sides, you get x equals x to the 6. And it might just be easiest to solve this by inspection, just by looking at it. What number could you put in here and here so it equals the same thing? Well, if you put 0 in there, 0 equals 0 to the 6, so x could be 0. And if you put 1 in both of those, it would also work. 1 equals 1 to the 6, so x equals 1. Now when x equals 0, what's the y value in this case? Square root of 0 is 0, 0 cubed is 0, yep, that worked. If x equals 1, what's the y value? Square root of 1 is 1, 1 cubed is 1, yep, that worked too. So there's your points, right? The kind of the boundaries of the area you're interested in. We want to go from 0 up to 1, we'll put it way up here. We want to go up to 1 here. So they're going to share a point here and here. Now, what happens in between there? Well, if you think of what the square root graph looks like, it actually goes up like this, right? It goes like that. That's this one. And then in a different color, I'll draw this one, x cubed. If you're not sure, put something like 1/2 in there. If you put 1/2 and you cube it, you actually get 1/8. It actually goes quite small. So it's going kind of the opposite direction. It's going like this. And what you're interested in, again, is the area in between those. So you're interested in that, and you're rotating it around the x-axis. So this is the axis of rotation. And then the last thing we want to draw is our representative radii. And remember, that's going to be parallel to the axis of rotation. You can draw it where you want. I'm going to draw it, I don't know, right here. As long as you draw a parallel line somewhere in here, you're good. Okay, we're ready to write down our formula. Okay, v equals 2 pi. So everything's in terms of y now. We want to look along the y from the lowest to the highest. Well, that's from 0 to 1. Those are our bounds. 0 to 1. Next, this y. Remember, what this refers to is the distance from the axis of rotation to the representative radius. That's this distance right here. Well, since it goes right from the x-axis, we could just call that y. And that's always going to be the case for this year, I promise. It'll just change next year if you're rotating over some other line, like some line around here or something. Okay, now we need a function that represents the length of the representative radius, this length here. Well, that's actually kind of tricky, isn't it? Because you have to take both of these functions, the green function and the blue function, into account when you want to figure out how long that is. The length of that would be equal to the x value of the green, remember the green's this one, take away the x value of the blue. Okay, well that takes us to another point. When we're rotating over the y-axis, everything has to be written in terms of y. Right now it's not written in terms of y. It's written in terms of x. So we got to change both of these. Sorry, I should never do this, but I'm going to erase this and I'm going to rewrite these in terms of y. So if you square both sides here, you get x equals y squared. Okay, great. So that describes this blue one right here is just y squared. Now this one, if you took the cube root of both sides, you'd end up with x equals the cube root of y. And great, that's what we can write down for this one, cube root of y. So if we want to know the length of this representative radius, whether it's drawn here or up here or down here, what we're always going to have to do is take the green one, that function, and subtract the y function, and that'll always give us the length here. So that's what we're going to do. We're going to take the cube root of y, but wait a minute, rather than going cube root of y, why don't we write y to the 1/3, right? This is actually the same. This is the same as y to the 1/3. So we'll go y to the 1/3, and then we're going to take away the y squared. Why did we not do that in the last one? We didn't do that in the last one because look, our shape went right down to the x-axis. So it's kind of like we were doing our x cubed plus x, which is the blue, take away 0, because it's right on the x-axis. Okay, so here is our definite integral that we now need to solve. The hard part's over, right? Getting to this point is the part that causes so many problems. So v equals 2 pi, 0 to 1. Let's multiply distributive property. Add the exponents. We got 1 here and 1/3 there, which is 1 1/3 or 4/3. So y to the 4/3 minus 1 and 2 is 3. And we're going to integrate in terms of y. Let's actually integrate now. 2 pi. So we're going to add 1, or 3/3, to get us up to 7/3. And then we've got to divide by the same amount, 7/3. Minus, add 1 to get up to 4, and divide by the same amount. And 0 and 1 are our bounds. So v equals, I guess I should simplify this first thing, shouldn't I? So remember, when you have this fraction over fraction, this denominator here is going to pop up to the top. So you actually get 3y to the 7/3 divided by 7 minus y to the 4th over 4 from 1 to 0. And 1 and 0 are beautiful numbers to plug into fractions. So let's see what we get. We plug 1 in here. 1 to the 7/3, 1 to the anything is still just 1. So we got 1. 3 times 1 is 3, divided by 7, we get 3/7. Minus, put 1 in here, 1 to the 4th is 1, divided by 4, you get 1/4. Then minus, put 0 in here, it's 0. Put 0 in here, it's 0, so there's nothing to worry about there. Just have to do these first fractions. So common denominator is 28. Multiply top and bottom by 4 and you get 12. Multiply top and bottom by 7 and you get 7. What the heck, I'm going to save some steps. I can cancel the 2 and the 28 and this becomes a 14. And I'm ready to write down my final answer. 12 minus 7 is 5 times pi is 5 pi. And now it's over 14. We are done. We have found the volume of the shape that's formed when you rotate this yellow area around the x-axis. It's incredible. I can't even picture what it looks like. And I figured out the volume. Good job, everyone.